MarkToda. He'll be speaking about modern smart contract design and security without compromise.
Hello. Good morning. Yeah, I'm MarkToda. I'm a protocol engineer at Uniswap Labs. I'm sure many of you saw that we released our Uniswap v4 protocol a few weeks ago. I'm going to be talking about it today. I only have about 10 minutes, so I'm going to be giving you a brief overview of kind of the architecture of Uniswap v4, specifically talking about our singleton and flash accounting pattern and how it sort of affects the security of the system. Okay, so kind of a standard design principle for smart contracts, and one that Uniswap really cares about, is this idea of sort of defining your invariants and enforcing them explicitly and tightly on your smart contracts. And sort of a famous example of this is the xy equals k curve from Uniswap v1 and v2. There's like a single line of code where we're enforcing the invariant, and it sort of ensures the security of the Uniswap pools. And sort of one important thing to note about the way that we sort of traditionally have handled these invariants is sort of that they use the smart contract as like the base unit for invariant checking, right? Like one pool in Uniswap v1 and v2 and v3 is one smart contract, and the invariants sort of apply to one pool, and so any operations over that pool, the invariants are enforced, and like each pool is sort of its own set of invariants and its own checks. And this is a really nice abstraction for smart contracts because it makes them quite easy to audit, right? Like every smart contract has these things that you can verify and things that you can test. It makes it quite a bit easier to reason about changes to the protocol as well. And sort of the asset positions, specifically for Uniswap, are segregated by pool, which allows for some nice checks. But it does have a few downsides, which I'll try to explain here. One is that there's sort of, if you're performing operations over the Uniswap protocol that affect multiple pools, then there's some intermediate checks between the different pools that have to be done, which can cause some gas inefficiency. It's also hard to do more than one operation at a time, and I'll give examples for both of these. So here's an example where someone is doing a swap across two pools on Uniswap. This could be Uniswap v2 or v3. So for example, here they're swapping WETH to DAI, but there's this USDC intermediate step. And so the first thing a router will do would be to swap WETH for USDC on the WETH USDC pool. And because the invariance and the logic is handled contract by contract, pool by pool, the WETH USDC pool checks the curve and sees how much USDC the user should get for a certain amount of WETH and sends that back to the router. And then the router has to do the second stage separately, where it goes and talks to the USDC DAI pool, sends its USDC there, and it swaps for the DAI secondary pool, checks for its invariance sort of separately, right? And so the key thing to note here is that this USDC is kind of like an intermediate operation in terms of the protocol itself, but because each pool is handled separately, it has to be sort of fully settled in the middle, right? So this USDC is like transferred back from the protocol to the router and then back to the protocol. So you can see how that's kind of a potentially inefficient extra step. Another example here would be if we're trying to swap and add liquidity to one single pool. Like if we just had one side, if we had just WETH and we wanted to add liquidity on WETH and USDC at the same time, it's one pool, but it's two operations on one pool, and the invariants are checked operation by operation as well. And so the router would have to send the WETH in, swap it for half of it for USDC, and then send them both back to the pool to add. And so again, you see this intermediate step with the USDC that potentially is unnecessary. And so as we were sort of thinking about designing a new protocol, we were thinking, how can we improve this trade-off while also making it easier to interact with the pools, easier to build integrations, and also maintaining this sort of invariant checking system. And so the first thing that we did, which seems kind of like the main way to do this, is to make Uniswap a singleton as opposed to like a multi-contract system. And so in Uniswap v4, there's one single contract that holds all the pools. We call that the singleton or the pool manager. And so all pools live on this contract. Instead of being separate contracts with separate asset balances, all the asset balances are shared, and the pools are handled by a struct and a library construct that handles all of the curve math. So each pool is still able to maintain its invariance and maintain the balances of its curve using that library and struct construct. But we have the ability here, as you can see, to kind of perform multi-pool operations in the same smart contract. And the way that we actually do this is using an interaction pattern called flash accounting, which is specifically enabled by a new EIP called EIP 1153, or transient storage, which is not out yet, but it should be out in the next hard fork, Cancun. And so the basic pattern of flash accounting, and again, I'll go through an example of this, is that the router can still make calls one by one, operations, swaps, and add liquidities across different pools. Each pool still asserts its invariance on each operation, but instead of settling them right then as the operation occurs, they sort of store the delta, or they store like what needs to happen for these operations to be valid. And as all these operations happen, those deltas kind of aggregate. And only at the very end, when the router or the integration is done operating on the pool, is everything fully settled. So I'll explain an example here. So here we have like a router, and we have the v4 singleton pool manager, which has many pools. So it's going to be the same thing where we're swapping WETH for DAI with USDC in the middle. So the first thing the router will do is call a function called lock on the singleton. And lock is sort of the way that you start this context, or that you start this like multi-operation transaction. And so calling lock does two things. It sets up a lock accounting context on the singleton, which is a transient storage mapping basically of two sides, like debits and credits, where one is tokens that the pool is owed for the operations to be valid, and the other one is tokens that the pool owes to the user that they can take. And then the singleton calls a callback on the router, which lets them perform operations under this context. So first operation here might be, let's swap one WETH for USDC. And what happens in the singleton when that operation is called is it talks to the pool construct, which is just like, it operates pretty similarly to a Uniswap v3 pool. And the construct will say, okay, if I get one WETH, I can give the user 1,800 USDC based on the curves and the liquidity and so on. And then the singleton will add that sort of delta to the lock accounting. So in this case, it says, I need one WETH because that's what the user was swapping, and I owe the user 1,800 USDC. And then if we do the second swap here, where we're swapping 1,800 USDC for DAI, we'll talk to another pool, and again, that pool operates independently using the library instruct construct. And it says, okay, if I get 1,800 USDC, I can give the user 1,800 DAI. And importantly here, those deltas cancel out. So when the 1,800 USDC is sort of given to this USDC DAI pool, it cancels out from the lock accounting because it was an intermediate step. And now the lock accounting says, okay, I need one WETH, and I can give 1,800 DAI. And now the router can call a function called take, which literally just takes from this O side of the lock accounting, and it pulls the tokens into the router. And then there's another operation called settle, which is basically like you send in funds, and then it settles the need side of the lock accounting. So the router might send in one WETH and call settle, which would clear out the lock accounting. And then once the full lock call is done, the singleton essentially needs to just check, like, is everything settled, right? Are all of the deltas 0? And if so, then we know that every pool was satisfied, and the full swap, the full operation was done properly. And so, yeah, again, transient storage is really important here because, as you can imagine, all of these operations and all of this accounting is happening on every call, like separate calls. And so if we had to do this before transient storage, it would be full S stores for every delta. And so with transient storage, because these are sort of only temporary state, it's only needed for the context of this operation, we can throw it away afterwards. And transient storage is much cheaper for that operation. Also, this is quite flexible in terms of operations or in terms of integrations, because you can call many operations on many pools in whatever order you want, integrate with other external protocols as well. Makes it quite easy. Also, yeah, the invariants are still managed tightly by the pools, so we can like buzz test and formally verify those pool constructs, which is a nice security principle. Okay, that was it. It's very short. There's many more talks on Uniswap v4 at ECC. I put a few of them here. Yeah, go see them. Thank you.
Thank you so much, Mark. So who has questions about Uni v4? Oh, there's a lot of questions. Break you the mic.
Hi, thanks for the talk. In terms of invariant check, usually it's encouraged at the end of the operations, and it's great for the protocol itself. But do you think it opens other attack vectors because it it basically ignore the middle steps in a largely sense? For example, read-only reentrancy. And what's your take on that, and how should we deal with that?
Yeah, that's a good question. I think from my perspective, kind of if I'm not sure if you've read the code, but it's quite similar actually to the code of Uniswap v3. It's just instead of being the whole smart contract, it's a library inside of it. And so basically the only change to the ways that the invariants are handled is that instead of checking the required tokens in and tokens out after a swap, they just get added to the deltas. And so from the perspective of a pool, as long as the deltas are being satisfied properly throughout the entire transaction, all of the invariants are satisfied. If that makes sense. I think the sort of reentrancy and multi-operation flow is actually pretty unchanged in this case. Yeah.
Hello.
Hi.
So how do you handle tokens that do weird things in this new model of only one single pool?
Yeah, that is a good question. Again, it's actually pretty much the same as Uniswap v3. You can make a Uniswap v3 pool with any random tokens you want, and maybe the sort of behavior of that pool is undefined in that case. And that's the case on Uniswap v4 as well. But because the sort of logic and state and checks of every pool is segregated within the singleton, it still actually doesn't affect the solvency of the pool as a whole. Or pool might have less tokens. What do you mean by that?
If somebody, if weird behaving coin actually removed your balance or increased your balance, the pool's accounting, the total accounting might be off.
Right. Oh, right. I see what you mean. Yeah. That definitely would be true, but it would only affect other pools that also have this weird token, which affects balances, right?
I'll catch you later.
Okay.
Cool. Any other? Sorry. That's it. Is Jeremiah here? Yeah. Awesome. Well, thank you so much, Mark. Let's give it up for Mark again.